Good morning, everyone, and welcome to the Go Fly Master webinar lecture this morning. To kick us off, I'm going to pass it over to Gwen Leiter, CEO and founder of Go Fly Prize. Gwen?
Hello, everyone, and we're so pleased that you are joining us today. We have a very special master lecture for you with Dr. Bill Lewis. As you all know, Go Fly's grand sponsor is Boeing, and we are joined by over 20 different aerospace organizations and engineering and STEM organizations throughout the world. And together we all bring you this master lecture today by Dr. Bill Lewis. Dr. Lewis is Director for Aviation Development at the U.S. Army Aviation and Missile Research. And he is he's been selected for senior executive service, or was selected in senior executive service in July of 2006. The Director for Aviation Development manages and directs the execution of the Aviation Science and Technology Program, including basic research, applied research, and advanced technology development. So Dr. Lewis provides direct leadership of the Aviation Applied Technology Directorate, the Aero Flight Dynamics Directorate, and the Aviation Systems Integration Facility. He is responsible for the success of the Army's multi-million-dollar Aviation Science and Technology Program, and is the Office of the Secretary of Defense Lead for Rotorcraft Technology. And to add to all of this, Dr. Lewis is was an experimental test pilot in the Army, he's Army Program Manager, a professor of the University of Tennessee, and he led the Army Airworthiness Program during the recent conflicts. So without further ado, I am so pleased to welcome today Dr. Bill Lewis.
Okay, thanks, Gwen. It's great to be here. It's great to talk to everybody. I want to start this out by saying, hi to all the Websters out there for Go Fly, and get ready to talk a little bit about what it is that I think is really important. Given the fact that I've managed many programs for the Army, and also when I was a professor at the University of Tennessee, we had a flight research office. So we managed many smaller programs too, programs that maybe weren't as well funded as the Army programs, or as large as the Army programs, et cetera. So I just wanted to shed a little insight on some of the critical parts of that. And I'm going to ask hey, Paul, I'm not seeing my talking head up here. Is that a problem with the web?
Nope, you're all good.
Okay, good. Okay. So one of the biggest things that I think is critical in understanding how to operate one of these programs is to understand what kinds of things are going to keep you from success. And in our case, in this Go Fly process, it's really going to be about the technology and the integration. As a matter of fact, when I was the lead for the Comanche program, for the technical parts of the Comanche program, I had a little tagline that said, "It's the integration, stupid." And really was the mantra that I had to follow throughout that whole process, to make sure I had the right kinds of tests laid in. I had the right kinds of sills to experiment with different parts of the development effort, to make sure that I was on the right path as we accumulated all of the elements to get a system level process. And I think you have to remind yourself that it's the system that has to succeed. It's not a component of the system, but overall, if the system doesn't come out at the end because somebody didn't deliver something the way they were supposed to, or we crossed some wires during the integration, all of that is a failure at a system level that you have to be able to avoid. So really the issue for me is all about tech dependencies. And as the chief engineer for Comanche, I'm here to tell you that one of the problems that we had with Comanche got canceled in like 2004. And one of the reasons were we had tech dependencies that were kind of stacking up on each other. So there was no way that we were really able to get through that process on schedule, on time, budget, et cetera, without some of those things coming to fruition, and it just wasn't going to happen the way we had it laid out. So the point I want to bring out to you folks is it's extremely critical that you define your tech dependencies. Now, for those of you out there who say, hey, we've thought about this problem and we don't have any tech dependencies, you have to understand that you just don't realize you have tech dependencies, because tech dependencies are going to occur. There's no way that you can start a program at the beginning and go all the way to the end without tech dependencies. If you say that you're doing that, either A, you're paying too much money, it's taking too long, et cetera, because that is part and parcel to how you efficiently manage these programs, these technical programs, as we go forward. So what I've done here to talk a little bit about tech dependencies and a little bit more about the systems engineering process, I've kind of laid out a little scenario that talks a little bit about what were some of the things that we're fictionally taking a look at within the Army. This is not a program, but it's just some little elements that I think present some of the kinds of things that you're going to bump into as you work through your technical program. So I've got an outline here, and it kind of walks through what it is that I'm going to talk about. So Paul, if you go to the next slide, I appreciate it. So as I take a look at this, the Army right now, we're at a case where we do manned-unmanned teaming, but predominantly it's one-on-one. We're able to control the sensor of a unmanned vehicle from inside the aircraft, and we can look around and do things. And eventually we're going to be able to command those systems, maybe one on many, and then farther on down the line, we're going to have autonomous systems on demand for various missions. I mean, the mission doesn't have to be just a surveillance mission. It can be resupply, reconnaissance, you name it, and parts of those can be broken up to take a look. It may be one aircraft, it may be a swarm of aircraft. So as you start to take a look at, okay, this is the objective. How do I then get into the kinds of things as an engineer, as a developmental engineer? How do I get into the things that are really important for me to understand as I start to move forward? So next slide. So you kind of have to understand what the pieces of this thing are. I mean, there's a system engineering piece, and then there's a project management piece, and there's some overlaps between those. But basically, the systems engineering piece is all about the discipline of designing the system, whereas the program management piece, the project management piece, is more about some of the constraints you have to manage, cost, schedule, performance, all those risk elements that are a part of that. Now, I'll say this, if you take a look at that systems engineering chart, it talks about an integrative discipline, it's iterative in nature, those kind of things. I've often said that the best systems engineering process in the world has really knowledgeable engineers involved from day one. And why do I say that? The systems engineering process academically is a iterative process. You go through and you find out what you missed or the things that didn't turn out the way you wanted. And so you redesign, you go through, and if that doesn't work, you redesign. There's no replacement for a bunch of experienced engineers to say, hey, we've tried that many times, and we're not going to do A, B, and C. We're only going to do D because we know that that is the path to success. All those other paths will lead to failure. The more of those smart people in the room you have, the less iterations you have. And remember, any one of the subspecialties that you're working with, aero, mechanical, electrical, whatever they are, any one failure is going to cause a system failure, which for you is a failure. So you have to understand that, and you have to get those people in the room. Now, when I was at the University of Tennessee, I taught a course in fundamentals of VTOL design, powered lift airplanes. Okay, and you take a look at the powered lift airplanes, and you start talking about what configuration should I use? Because historically, in a lot of the motion picture elements, you see aircraft that have lift engines and then thrust engines. Historically powered lift airplanes. We've tried to develop aircraft that had lift engines and thrust engines. Now, separate functions within that requirement. And what we found over and over and over again is if you have separate lift engines and propulsive engines, that may not be the optimal solution for a configuration going forward. So now you got to pause and say, well, wait a minute. If I've got that configuration, how am I going to, get back to, take a look at my tech dependencies? Because my configuration may be my very first tech dependency. And some of these things get so bad that you actually have to go back and redesign the whole vehicle or choose a different configuration to get after the things that you need to get after for performance and cost, et cetera, as a part of that overall effort. There was a mantra as a part of that was, tilt the thrust, not the vehicle. So something that, articulates, and, I've got some of these here in the background as a V-22, obviously they tilt the thrust as a part of their program. F-35 with their nozzles, they tilt the thrust. So as we look at these solution spaces, negating scalability, as we look at these solution spaces, the things that have seemed to work in the past have been things that actually tilt the thrust. So that may be a configuration that is of interest to you. So going forward, the first thing you got to take a look at is, okay, what configuration do I have? Do I understand the pitfalls or the failings in the past of the configurations that I have? And if you haven't seen Mike Hirschberg's, Wheel of Misfortune for VSTOL aircraft, you need to grab a copy of that and take a look at it, because just about every configuration that you can imagine has been tried at some point in time, at some size, at some snapshot in time for the technology piece that we had, and take a look at what worked, what didn't work, and why, those kinds of things. And if it's something that you can fix, if it didn't work because of structure, but now you have a better structure solution, then maybe your configuration is still good to go. The other thing I would be very, very careful of, cautious of for a tech dependency is, just because it worked as a really small demonstration or a beta aircraft, it may not scale to the size that you need for it to scale to be a solution space for you. I mean, it may be about strengths of materials. It may be about Reynolds number matching. There's a whole lot of issues associated with whether or not it'll scale appropriately. So you have to be, a lot of times in these vertical lift vehicles, it's about dynamics, the interactive dynamics associated with those big rotating masses that we have and those kind of things. So something else to think about as a part of your configuration design and your testing to get to a full size vehicle. So, but again, that systems engineering process is really the design process, discipline process you have to walk through to take a look at what's my output. Is it going to be a demonstration? Is it going to be a production vehicle? How am I going to manage the tech? Operationally, how am I going to operate it? For us, a lot of it's about, we got a whole life cycle. So how are we going to eventually retire the aircraft and get after those kinds of things? I will say this before I get too far into the specifics of the vehicle design. There's a lot more to this operational piece than just about designing a vehicle. Some of it's about, is the infrastructure going to be ready to accept your vehicle as a part of that? Now, I understand we're doing a prize here, so everybody's probably going to be involved in this in experimental fashion, right? So, but the real issue is, if you're trying to mature this into a vehicle that's going to be able to operate an Uber kind of thing or something along those lines, package delivery, whatever the mission set is that you're trying to solve, you have to have infrastructure. And if you don't have infrastructure, the problem is that you're probably not going to be able to operate the vehicle. I was out in San Francisco about 3 weeks ago, and we had a eVTOL design conference out there where I think the comment was there will be 64,000 eVTOL operations within a 40 nautical mile radius of San Francisco. That's a whole lot of aircraft operating in a relatively small space. So how do we get after that infrastructure? And, oh, by the way, I'll talk about, and what about the airworthiness? You're going to have to get a vehicle that's safe to fly. I think it was Chris Van Buten from Sikorsky made the comment of these vehicles, especially when you start carrying passengers, are going to have to be an order of magnitude more reliable, at least, than our current aircraft. Our numbers, we use 6 nines, it's 1 in a million, right? So, but he was talking 7 or 8 nines as the objective to get after for reliability. So if you haven't considered that, that may be a dependency that you have that's just laying out there and wait that you haven't realized yet. So definitely look at infrastructure. Definitely look at certification. And back to infrastructure, when you talk about that, say we have a free flight kind of philosophy. I won't even put it in a constrained environment, a very controlled environment. Say you got a free flight philosophy. Well, you're going to have to see and avoid. We haven't been able to crack that nut yet. I mean, we still don't have the system that we think is the right answer for see and avoid. So you're going to have to put something on your air vehicle that has the capability of see and avoid. Algorithms, hardware, software, the whole 9 yards integrated that you may or may not have planned for, right? So that whole issue of swap and how you manage your swap is critical. Just talk about swap for a minute, because as we go forward, these vehicles are going to be relatively small and densely packed. So size of components and size of vehicle is going to be very, very important. So that's always got to be deliberately managed by component. So now we're rolling in configuration management processes that you ought to be tracking, weight. The one thing that we track on every aircraft that we ever develop is weight. And typically we build a weight budget, and then we do, we have allowance for growth and some of those kind of things, but we want to be able to deliberately manage the weight component of that, because, lift's equal to weight. And the lighter it is, the easier it is, the less power it requires, and it just gets easier that way. So once you get into that weight spiral, okay, so now if you're saying, okay, I've got 1 engine, okay, great, we're designing aircraft. Now if you say, no, I need 2 engines, okay, now you've started the whole, what I call chasing the design point, because now the overall weight of the vehicle is going to go up, because now you have more weight in the engines, more propulsion system, more weight in the batteries, or hybrid, however you're going to do it. So all of those things become a very deliberate process, to the point to where we've handed out, for sure, coffee cups, but leather jackets. I mean, save me 10 pounds, I'll give you a leather jacket. I mean, those are the kinds of deliberate methodologies that you have to go out to and implement to be able to get around some of these tech dependencies that we're talking about in terms of weight savings and weight management, fundamentally. And lastly, power. A lot of folks are doing, well, I call it electron agnostic. I look at it electron agnostic and from the standpoint of, I don't want to depend on the battery power. If the batteries get to the levels that they have the right kinds of power, the power loading, great. But all of the numbers that I see for power loading are 10 to 15 years out from where we believe our systems will be able to take advantage of that. You're looking at lithium metals, you're looking at a whole bunch of technologies that have to mature to get you the kinds of things you need. And even if you're getting the power, you don't want it to be something that'll explode. I mean, in this business, we're worried about people shooting us, and sometimes those fuel cells, those batteries, et cetera, are hazardous contribute to a big hazard if they get shot, or just if they overheat, over temp, and get back to the whole issue that we've had with lithium ions, et cetera. So when you go into this electron agnostic, you better start thinking about, okay, what okay, where are the electrons going to come from and how we're going to work on them, and, you know, et cetera. So whether you're doing hybrid or whether you're doing batteries or whether you're doing, you know, burning fossil fuels, you know, whatever it is that you're deciding to do, make sure that you understand all of the things associated with that and the tech dependencies, not just of your engines, but of the associated equipment that's going to be out there. That may drive your schedule so far that to the right that you may not be able to accomplish your mission in the kind of constraints that you're going to have from a project management perspective. So, okay, Paul, next slide, please. So how do you determine what these tech dependencies are? And for the systems engineers in the room, I apologize. This is just some basic 101 stuff, but for the folks that, you know, maybe are a small company, that kind of thing, you know, if you haven't thought about it this way, you may want to pick up an SE book. Everybody's got a different way of kind of lining this stuff up and getting after it, but I'm just going to walk through basically a simple process. When you take the big task at a system level, you break it down into a work breakdown structure that has various levels of effort involved with it. So then you say, okay, what is going to take the longest to get from point A to point, in this case, X, okay? And why is it that it's taking that long to get me from point A to point X? There is something in that path that is going to be the critical elements that extend the length of the program. If there's not, then you either got way more money or way more time than you should have to develop this vehicle. So you should be tracking critical path. Without getting into all the details about critical path, there's a lot of discussion about, you know, do you track it to the WBS 3 level or to the 5 level? Does everything have to be tracked? My personal opinion is you track everything to a level that you got some visibility on it. And then for the things on the critical path, you probably drop down a couple more layers to get after the kinds of things that may be the critical technologies that you need to develop to be able to solve the problems. But there should be something in this program that puts you on a path that you understand. If the batteries don't come through, I'm not going to make it. If the engines don't come through, I'm not going to make it. If I can't make this work from a performance perspective to go as fast as I need it to, that's not going to work. I mean, there's a lot of things that get after that system solution that you have to understand and you have to deliberately manage. Now, if you're going to operate this in airspace, you could probably also put some less technical things on there in terms of infrastructure, in terms of, certification, those kind of things as well. And I think what you'll find out if you do that is that the technology is going to be much, much, much quicker than the regulatory elements of that. It's going to be much, much quicker than the infrastructure development and implementations of that. So just understand that you should be out in front of those kinds of things. The technology is going to be relatively quick once you get on your path to accomplishment. So, it's more than just scientists, engineers in a room coming up with a configuration. A lot of it is about, the bureaucratic business processes, et cetera, to get after the kinds of things that you need. Okay. You can take a look at this little scenario, and you can tell that, okay, there's certain elements that are on a critical path, et cetera. So you should be monitoring those. If by chance one of those elements transitions faster than you thought it might go away. It might not. It may no longer be the critical path. Something else may wind up being the critical path after that. So those are the kinds of things that you're trying to accomplish. How do I get these technical dependencies, time, cost reduced so that I can track through this with minimal requirements, problems, minimal developmental problems that I have. So, okay, next chart. So again, just trying to understand how to manage these is really important. when you start a program, you probably select vendors and you probably look at the kinds of things you think are the right answer. Maybe some of that study is based upon algorithms or theory. I know that when you're dealing with rotorcraft, we have figures of merit, things that say, ideally this is the amount of power that's going to be required to hover, say. Well, in actuality, you got to start compensating for other things that are in there that do not match the ideal. You may not have uniform flow. You may not have, the kind envisaged air. That's hard to find, by the way. So all of those things that you have as assumptions will then reduce from that ideal some level. So maybe you're assuming it's going to be an ideal solution. That's what the model said. And then you find out it's really 10% more than that. So obviously those things are going to keep popping up throughout your testing, throughout your progress, through the development design of the vehicle. You may find a vendor can't give you the kind of components they promised as a part of the overall process. I recommend strongly that whether your vendors tell you, I'm giving you this and it has this much tolerance, this much performance, that you verify that independently before you assume that that's the answer. Because a lot of times what you'll find out is, hey, the tolerances are a little more than what they said, or we're not getting quite the efficiencies that they advertise. And then there's always a problem of, tolerance stack ups and those kind of things that may push you out of the window of acceptable performance or reliability for those kinds of things. So again, monitor all of these elements, try to reduce them, understand them, dig down deep into the ones that you know that are going to be technical dependencies, and try to get the right answer for those things. What do I mean by that? Well, we were designing detectors for forward-looking infrared systems, and of course you build a detector. It's got pixels on it, and you can supercool it so you can see temperature deltas, that kind of thing. And so you say, okay, well, we've done this several times. Well, one of the things that happened as a part of that was they changed vendors for the glue that was used to put the wafer together that has the pixels on it. Well, that glue started to be a problem, and it started to have, manufacturing aging problems. You started to pull apart. And then all of a sudden, what we thought wasn't a technical dependency, all of a sudden became a huge dependency on being able to find another source for the kind of performance that we spec'd out in the very beginning of our program. So again, this is not a one-time snapshot thing. This is a continuous process, working with your vendors, working with your integration folks, working with your testers, your SILs, to understand the problems, understand the solution space that you have, because it's all about this balanced design. It's all about trading solution space back and forth to get after what you need. So, okay, next chart. So now you've identified some of the things that are going to be problematic. So what do you do about it? Okay, yeah, we know a battery is going to be problematic. We know it's going to take 10 years. So is that going to be our answer? Is batteries going to be our answer? What else? How are we going to do that? So you take a look at and let me explain this a little bit. This is a process. This risk management process is part of a standard. In the government, we got standards for everything. It's part of a standard that we utilize. It's called 882. It's actually a risk management standard, and basically it's all predicated upon how often it occurs and how bad is it going to be if it occurs. So if it occurs very, very often, I mean that's a 5. And if it's really bad when it happens, that's a 5. So you want to drive everything down to the 1-1 box, right? So that's really in order to eliminate the risk or mitigate the risk as much as possible. So you take a look at what the technologies are and where you are in the box, and then you come up with workarounds, lack of a better term, alternatives, workarounds, understanding, knowledge, to drive these risk elements that you have to the left and down. Okay, so we worked this example so you can take a look at the kinds of things that we were talking about with each one of these things. And later on, you can go in and say, okay, 3 was this, 1 was that, you know, those kind of things. So you start working down and trying to come up with alternatives to mitigate this risk. And sometimes it's easy and sometimes it's really, really hard to do. Okay. But if you don't identify these on your critical path and you don't deliberately take a look at them, I mean, some of them are obvious, some of them aren't, and you don't understand the impacts that they're going to have if they don't mature at the rate at the time, you know, because a lot of times it's about how fast they mature to a schedule. You know, if they don't mature in time, then you're going to be sitting there waiting for something else to happen. And that, of course, that blows your schedule, and your probably your funding. That's part of the problem. So you don't have to use this approach. This is the approach that we use. You don't have to use this approach. You can do anything you want to. You can do a 1 to 10. Make up your own approach. But just understand that what you're trying to do is, by virtue of using this simplistic methodology, understand the dependencies you have and try to reduce them through alternative means of a solution space. And again, that kind of gets back to what I talked about, agnostic electrons. Yeah, I'd love to have batteries and you know, electrical motors to do this thing, but if the batteries aren't there, do I have an alternative for a hybrid system? What kind of engine would that be? What are the issues with the engine I want to run? Is it a recip? Is it a turbine? You know, oh, guess what? I want a small turbine. They're really hard to build. They're really hard. You know, so you go through all these very deliberate, you know, thought processes to get after what makes the best solution for you. Okay, next chart. So, you know, this is kind of an explanation of some of the things that I just talked about in the path. Now, typically these things don't migrate across a diagonal. Typically they'll migrate incrementally left to right, up to, you know, from top to bottom. That's the most common way to do it, unless of course, there's some disruptive technology that all of a sudden comes on the market. All of a sudden, somebody comes up with a battery that solves all your problems. Man, you just leap from, you know, the upper right corner down to the, you know, lower left corner. That doesn't happen real often, okay? Typically, you're going to incrementally improve, and you're going to be tracking all that, and you'll see how your elements are migrating. But sometimes you'll get, basically you've painted yourself in a corner. So you got choices either to redesign or try to get different components to get out of this risk box that you're in. Because the last thing you want to be is in a corner where you have no options and you're just waiting for something to happen. So how do you buy that down, right? Now, some people say, okay, well, it's all about the technology. Well, we don't do it that way. Sometimes we say, if I build a vehicle that didn't quite meet the requirement that I was shooting for, and I work with the people that are going to use this thing, and we can come up with a solution through training, through doctrine, through operations, facilities, you know, those kind of things. All of that works as well, okay? But we have kind of a captive organization in DOD. You know, we kind of understand what we have to go to the fight and those kind of things. So for us, sometimes we know how big our hangars are. We know how our soldiers get trained. We know doctrinally how we're going to go out and fight the war, all those kind of things. Some of these, again, are undefined from a commercial perspective. If you're going to do package delivery, what kind of routing are you going to use? How's the FAA going to get involved? You know, what air traffic is going to be mandated or not? You know, do I still have to do all the things about C and B scene? You know, all those kind of things may not be as clean for you as they might be for an organization like the military. So all of those things are discussions about tech dependencies and ways to get after them. Again, I just want to, you know, for those people that are sitting out there going, now we don't have tech dependencies. No, you don't understand. You do have tech dependencies. You just haven't uncovered them yet. So as in order to optimize that development timeline and funding, you want a critical path. You want to be managing very deliberately the technologies that you're bringing in. But then the question is, how many technologies do you ideally want to have? And the answer is, it's an easy answer. It's zero. You don't want to have any technical dependencies. But if you don't, then you're settling for today's technology and today's integration ability, right? So if you're looking at something you're going to operate 15 years from now, that's probably an unsatisfactory answer. You're going to have to build in some of those tech dependencies to get after a better solution for the time frame that you're developing the vehicle. So I just, having done this a whole bunch of times on projects from small to really big, I just encourage you to work. This is homework. This is stuff that you have to sit down, brainstorm, bring your team together, and make sure that you understand everything that's in there. Sometimes you can solve this problem. Sometimes you can get around some of this stuff by hiring the right people. Okay, you may have some people on a team, but you don't have the right, I don't know, pick double E. You don't understand all of the things associated with heat and power and all those kind of things, right? Well, if you hire a good double E to come in and help you design that system correctly, may solve some of your problems, some of your tech dependencies. Not always that easy, right? A lot of times it's really hard, things that haven't been proven, haven't been done, process and infrastructure that haven't been developed, et cetera, to get after some of the things that you're trying to, design around. I'll put it that way. So I think that really, I got one more chart, I think, but this is kind of motherhood and apple pie for this crowd. Every time we do something, we do it based upon a life cycle, 20-year, 30-year life cycle. And of course you lock down all of your life cycle cost right up front when you decide what configuration am I going to use, what's my propulsion system going to be, how's my swap being implemented. All those things really kind of upfront locks down a huge amount of the total life cycle cost. And in this case, we're probably going to build one, maybe two aircraft, those kind of things for the test. But then if you take it to the next system to now want to sell it as a production vehicle, you just understand that whatever you decided in that demo aircraft, you're either going to have to modify into a production vehicle that has some of these considerations, or you're going to have to accept the fact that it's going to be expensive to operate because we didn't think about all that stuff in the beginning. Okay. Systems engineering wise, shoot for a 90% solution early to try to get it out there, understand all the problems you're going to have. It's not always easy to do that. Some of the things right off the gate, you'll understand are tech dependencies, and you gotta start digging into those fairly deeply. But if you're not using an approach like this, and you're not deliberately thinking about the kinds of things that can go wrong, you're probably going to pay a penalty for that at sometime in the development. So I encourage you to, I know some of these things are, very disciplined processes that require you to probably have more people or things as a part of the development than maybe you had ideally wanted. But over the years, we've found that if you don't do something like this, you will bump into problems that you hadn't anticipated, and you, at that point, you're kind of at the mercy of the technology development rate, the speed, etc. So with that, I think I'm going to stop and ask if there's any questions out there for me.
Great, thanks very much. Yeah, a couple of questions in already. So what does, on some of your charts you had wingman on there? Could you just explain what that meant?
Yeah, wingman, well, it's kind of, it's kind of just, in a combat scenario, it's, it's the guy that follows you around and does things. If you're going out partying at the bar, it's the guy that you take with you to kind of run traffic for you. But for us in the combat scenario, we want a wingman that we can offload requirements from the major platform onto our wingman. In the worst case scenario, if somebody shoots a missile at us and we can't avoid it, the wingman will actually take the shot. It'll actually position itself to take the round, right? So it's kind of the R2-D2. It's another vehicle that's kind of doing some of the R2-D2 kinds of functionality, if you will. We typically design those for, I'll use the Air Force model. In the Air Force model, they've got 2 aircraft. They actually have 4, but they got 2 aircraft, 1 autonomous aircraft, 1 manned aircraft. If you want to go into attack mode and you tell the wingman attack, it will zip out in front of you and attack the enemy. If you tell it to drag, it'll fall back and protect your 6. So it is there to be a partner in the combat scenarios that we develop.
Great. And then I think some of the other slides said AIL or ALE on them.
Yeah, those were air-launched effects.
Great, thanks. You talked a little bit about it already, but if you could just expand a little bit about what your thoughts are on the differences between engines versus electric motors when it comes to building aircraft of this size and scale.
Yeah, well, right now it's hard to build electrics, right? I mean, we do some hybrid stuff clearly that's out there. In terms of the tech risk, a fossil fuel burning engine, recip or turbine, depending on size, right, is the lowest tech. Hybrid second, all electrics third. Gets riskier. In terms of reliability, I would say the one that's the most risky is probably the most reliable. I mean, an electric motor has a shaft, a couple bearings, and power that goes to it. I mean, it's a pretty simplistic system. Turbine engine is pretty complicated from that perspective. When you talk about turbines, big turbines are far easier than very small turbines. And when I talk about turbine size, a 400 horsepower turbine engine is a lot easier to build than a 5 horsepower turbine engine, right? We have a program going on right now called RASP, Reliable Small Turbine, Small Propulsion System. Reliable, affordable, small propulsion. And we're trying to come up with a turbine engine that is about 200 horsepower. So the companies that we're working with are building turbine engines that are down around 20 horsepower, 50 horsepower. But for most of the segments that we're interested in, we think 200 horsepower is about the right number. It's easier to go scalability. It's easier to go big than it is to go small. So we figure we're in a good design point at that. So I don't know if that answers the propulsion question, but.
Great, thanks. And then you talked a little bit about teams and putting together teams. At this stage of the Go Fly competition, some people might be working on a very small team or by themselves. Could you talk a little bit about any advice you have for putting together a team, what the right size team is, and how to pick what types of expertise to have on that team?
Yeah, okay, for me, I mean, this is just the way that I like to do it. Smaller is better. Some people like to, get teams that got 50, 60 people on them to go design something. I think that's too many. There's too many opinions in the room, right? And maybe the people that do that, I think, are people that do not understand the details of the technology, and they compensate by adding people. I think the right size for a team, if I'm building a helicopter, rapid prototyping a helicopter, if I got more than 15 people on that team, that's probably too many, okay? Especially in the design, because you take a look at it and you say, okay, what do I need? I need, if we're looking at one of these vehicles, I need somebody that understands aero. I need somebody that understands probably cyber physical systems to include all the electrical elements. And I need a mechanical engineer for sure. And then if you put, if those folks can also do program management, now you're starting to talk about individual capabilities, right? They can also do program management and configuration management and, budgeting and all those kind of things. This makes for long days and long nights. But that team can get a lot done. Bigger than that becomes just dependent upon how much throughput you need, what the skill sets are of the people that are there. It becomes kind of individual. I mean, if you really get down to it, the skills of each individual engineer and the amount, because it becomes a life issue, right? The amount of effort that you want to spend at work. Now, I say that because I visited Rocket Lab over in New Zealand about 3 years ago. Okay. And for those of you who hadn't seen, Rocket Lab has successfully launched, they do small satellites. They do what Elon Musk does with big satellites, with mini sats, okay, small satellites. And I talked to the guy that was working that program, and he had a pretty big program setting that whole thing up. And he said that he likes for his folks to work long days, 6 days a week, 10, 12 hours a day, because it was all about getting the thing matured as rapidly as possible. And if the people weren't there in a collaborative environment doing that, whether that's, in a lot of cases, my collaborative environment's electronic, but if you're not there sharing, working, collaborating actively, then he didn't feel like he was getting the most out of the human resources that he had. So that just gives you an idea. Some people work 4 or 5 hours a day. I mean, that's an individual thing. So it's, again, it depends.
Sure. And then on a potentially small team like this, how much do you think personalities play into the team makeup in addition to the expertise needed?
It's huge. I mean, obviously, if you have somebody on the team that is not adaptable or acceptable, he or she can't put up with that person over in the corner. Well, that's not going to work. And if you got a person over in the corner that's just aggravating the heck out of everybody, that's not going to work. So you almost have to have a shared objective and a shared mantra about getting after some of this stuff. I mean, for me, I've been doing this stuff since I was a kid. So, I guess that's a better part of 45 years. So, for me, it's a passion. So it's like, you get people that share that kind of passion and go after project X or project Y. Sometimes it's easy, sometimes it takes more effort, but you've got to be able to work together and get along. I mean, any engineer worth their salt is going to have to be able to get along with people and collaborate. So.
Great. And then a lot of major decisions probably have to be made to work on the design for an aircraft like this. Can you talk a little bit about the timeline involved there and when some of those decisions need to be made?
Yeah, sure. Well, first of all, you have to make decisions. You can't sit around and hopefully, have a committee to have a committee, right, to get a decision. I mean, you deliberately have to decide, this is the deciding body and this is how we're going to decide our answers. Now, some of those things are pretty easy. Some of them are dependent upon maybe a test that you're going to conduct. In other words, we're going to go out and test this system that we have to make sure it operates the way we think it's going to operate. And once we determine that, we'll be able to make a decision about X. Again, that's all part of your very deliberate program management process that you go through. So some decisions are easy, some decisions are harder. The hardest decisions you'll have to make are who's going to be on your team and who's not going to be on your team. I mean, it's a lot about people and things, and of course, unless you're Elon Musk or some of those guys, you got to worry about money. I mean, it's that kind of a business. So.
And then what about the difference between decisions that are binary yes versus no things versus things that are a continuum? Can you talk a little bit about that decision-making process? Yeah.
I mean, this kind of gets back into when I talked about the systems engineering process. The best system engineering process has got guys with a lot of experience, gals with a lot of experience. Because it's very, nobody, I don't think, in this business makes a, black-white decision, in terms of technology. It's always on some continuum, right? And how far do I want to press to be able to get this? They know what has worked in the past. They know what, given the tech considerations, what will probably work in the future. And those experienced people will always kind of give you a gradient of well, you could do it this way, but if you did it this way, you know, these are the issues. So I think that all these decisions that you have, because very few black and white ones, I mean, but you have to consider, you know, tech reach. You have to consider secondary, tertiary issues associated with that decision. And again, back to your people. Do you have the right people in a room to be able to make the right decisions at the right time? So.
And during your talk, you mentioned future infrastructure capabilities. Could you talk a little bit about how the design process might leave the flexibility for things that are unknown that'll crop up in the future, like what the infrastructure ends up being in the future?
Yeah, well, again, that gets back into your swap. I mean, I think what you wind up doing, and I always said the last thing I design on my vehicles is the electronic interface. In other words, what DC things, you know, get hooked up to what box, because that thing, as you go through your design, is going to change many times before you get to the final conclusion. So you sit back and you say, okay, I'm going to need to navigate. Okay, so how am I going to be able to navigate? And you can kind of project that. I mean, I can use GPS, I can use Doppler, I can use INS, I can use, you know, I can stare at the sun. I mean, you know, there's a whole bunch of ways to get after some of those things, depending upon the range and all that kind of stuff. You can develop algorithms to do that, but by and large, you have to, and we do this a lot, you have to allocate an appropriate amount of swap for that cyber physical thing that you're going to wind up putting in the aircraft to accomplish that. Now, is that on a motherboard? Is that a chip? Is that a box? I mean, those are deliberate decisions that you have to make in terms of getting after the you know, the swap required for those. But I think you can forecast a lot of that. So one of the questions I used to always ask when I was doing an aviation systems thing was, to the students, if you went into a country that had absolutely no infrastructure, no airways, no ILSs, none of that stuff, you know, very little aircraft development, how would you set up an aviation system to develop aircraft and fly through infrastructure all as part of a 2030 projection? So you're deliberately trying to get them to think beyond today into what might be and the technologies that would be applied.
Great. And then just one final question. What's your advice to people competing in GoFly? What's your biggest piece of advice for competitors?
Don't think you know all the answers. There's a lot of things out. I mean, a lot of great people are doing this, right? Don't get me wrong. But being able to I've been doing this for a lot of years, all these technical things, and I'm always amazed. I'll have an Apache transmission that all of a sudden, you know, something goes bad with it. And I say, okay, well, who understands this problem? And they'll bring some person into my office and they'll sit down and they have intricate detail about all of the things that affect that transmission and all of the, you know, tooth bending and lubrication and all of the detailed complexities associated with that. I didn't know that person from Adam before they walked in that room and started talking, and you're sitting there going, man, am I glad I got this person in here to talk to me. So as you go through this project, don't think that you got it all figured out. Go out, reach out, look for consultants, look for people to come work for you, whatever, that have a very, very comprehensive grasp of the problem, because you have to have people that understand comprehensively the design and people that understand the depth of the technology. So you can't afford to have all those people on your team all the time, but you can afford to go talk to them and get some insight into what's going on. So collaborate.
Great. Thanks so much. And with that, I'm going to pass it back over to Gwen to just say a couple of words in closing.
So Bill, thank you so very much for your insight and expertise. We all learned a tremendous amount, and we are so pleased that you were able to join us today. And to all of you innovators, keep working, and we look forward to seeing you again at the next Go Fly Master Lecture. Thank you all, and have a wonderful weekend.
Thanks, Glenn.